This is the nuclear chemistry unit. In this unit, we will be examining the atomic nucleus. We're going to be looking at what holds the nucleus together and what makes them so incredibly stable. We're going to find out why some atoms are unstable and what are the results of that instability. Okay, by way of introduction, we're going to contrast nuclear chemistry with conventional chemistry. In conventional chemistry, when a chemical reaction takes place, the nucleus of the atom remains unchanged. Some bonds are broken, others are formed, and no matter how violent the chemical reaction is, the nucleus remains intact. Only the electrons of the atom are exchanged. They're gained, lost, or shared. But in nuclear chemistry, the nuclei and their particles are involved. So the identity of the nuclei changes. So nuclear changes change the actual composition of the atom. It becomes a different element, as illustrated by these two examples, which we will look at later. All right, most atoms are incredibly stable. In fact, most atoms on Earth are about the same age, even the atoms in you. So you are as old as the hills, or at least the atoms in you are as old as the atoms in the hills. So where did you get the atoms that you are using currently? Well, you get them from the food that you eat. You eat food for energy, but you also eat it for nutrition and to rebuild cell parts. So the atoms in you come from the atoms in the food that you eat. Where did your food get those atoms? From the food that it ate, and so on and so on. So atoms throughout nature are recycled over and over and over and remain intact, unchanged over the eons. Now, when we talk about nuclear stability, the word stable means not radioactive, and unstable means radioactive. So what makes unradioactive elements or atoms so stable? So if you think about the composition of a nucleus, there are protons that are positively charged that have a very strong repulsion for each other. You have these two or more positively charged particles within the nucleus that are as close together as any two things can be, and they really don't want to be next to each other. So they want to get away from each other. But also within the nucleus are neutrons, and these neutrons possess a very strong force. In fact, it's the strongest force in nature. Now, scientists, when they named this force, their creativity kind of went on vacation. They called it the strong nuclear force. Very creative. And this strong force acts like a nuclear glue that overcomes this incredibly strong repulsion that protons have for each other. A nuclei is stable if it has just the right number of neutrons for that number of protons. And what this number is depends on how big the nucleus is. If there are too few or too many neutrons in the nucleus, then the atom will be unstable. Now, I'm not going to show you how to predict the exact number of neutrons it's going to take. I just want to show you a pattern. So if we look at this graph here, this line represents the perfect 1-to-1 neutron to proton ratio, which really doesn't exist that much in nature. For small atoms, we do get largely that 1-to-1 ratio for atoms smaller than atomic number 1. So from hydrogen up through element calcium, then you have that 1-to-1 neutron to proton ratio. But for larger atoms larger than element 20, as we increase the number of protons that are that close together, it takes a disproportionate number of neutrons to hold those protons together in the nucleus. So if we look at element number 60, which is neodymium, if we look at its neutron to proton ratio, it's roughly 80 neutrons for every 60 protons, so you get a 1.4 to 1 ratio. So how does the neutron to proton ratio change as atoms get larger? The neutron to proton ratio increases. It takes a disproportionate number of neutrons to hold those protons together. Right, this next section has to do with the key discoveries surrounding atomic radiation. And the first has to do with the discovery of radiation itself. And it's said frequently that this discovery was done serendipitously. And serendipity means that it's a happy accident. And there were parts of this discovery that were sort of accidental, but he had a pretty good experimental design. So Henri Becquerel was studying phosphorescence in uranium compounds, and he thought that the radiation emitted by these uranium compounds were X-rays, and he thought they were a form of phosphorescence. So his experimental design was rather simple. He would take these uranium samples and would coat them with uranium compounds and then expose them to sunlight, put them on windowsills, and he would put them on top of photographic plates that were in sealed containers, sealed with black paper. So there was no way that the light could expose the photographic plates, but he postulated that the X-rays would seep through the black paper to expose the photographic plates, and that this is in fact what happened. But then he had a spat of bad weather, and it was cloudy for several days. So he stuck the uranium samples on top of some photographic plates that were inside these sealed containers, and they were put into a closed desk drawer for quite a few days. So there was no sunlight possibly to expose those uranium samples. And still, surprisingly, and this is where the serendipity comes in, surprisingly, the photographic plates were still exposed. It was basically proving that phosphorescence was not the cause of this radiation. The radiation was just a property of the uranium, and that the radiation didn't diminish over time. These rocks could be left in drawers away from sunlight for days and days and days, and they would still emit the same amount of radiation. That left some people thinking that perhaps there could be energy it seemed like it was creating energy from nothing. And of course, we knew that's not possible, and this experimental design was easy to replicate, so they proved that this was a new form of radiation. And then he solicited the help of the Curies, his fellow countrymen, and they were able to isolate the radiation and prove that it wasn't X-rays, it was some new form of radiation. So he shared the Nobel Prize with the Curies for this discovery. So the Curies were the next, and easily Marie was kind of head and shoulders above Pierre, although he was a crackerjack scientist in his own right. But in terms of this research, it was Marie that really shined. And first off, they helped Becquerel to figure out what radioactivity was. In fact, it was Marie that coined the term radiation. But her most famous discovery was she was the first to isolate radioactive elements, to actually extract them from the ore. And the first two that she did were radium and polonium. Radium named after radiation, and polonium named after her native country, Poland. So what does it mean to isolate an element? Well, it means you take the ore and you treat it with painstaking processes. Now, I'm getting a little ahead of myself. The reason she was able to isolate, or what gave her the idea for trying to isolate these elements, was that there was more radioactivity coming from the pitch blende than could be accounted for by the uranium by itself. So she postulated there had to be one or more elements within this pitch blende. So what she did to isolate it is they discovered a long, drawn-out process of extraction that involved grinding it up and reacting it with chemicals, and then purifying it, and then more chemicals, and then more purifications. So they were able to isolate pure radium and pure polonium. In the process, they contracted radiation sickness, but since it was a new thing, they really didn't attribute their sicknesses and their symptoms to the radiation that they were working with. In fact, many of the early scientists in this field contracted radiation sicknesses and lesions and all kinds of problems. All right, the next discovery Comes from our favorite nuclear scientist, Ernest Rutherford. And we've already looked at this in an earlier lecture. He discovered the three forms of nuclear radiation, alpha, beta, and gamma, and some of their basic properties. So here's a reminder of what his experimental design was. He took a radioactive sample, put it inside a lead container with a hole in it, and then had aligning slits that he could use to narrow the beam of radiation being emitted. And then to test the nature of this radiation, he exposed it to positive and negative plates. And then he had a luminescent screen that would give off flashes of light when the radiation struck it. And somewhat straight on through, and he postulated, he called these gamma rays, and he postulated they had no charge because there was no deflection. And then those that were deflected away from the positive toward the negative, he said were alpha particles, and they're positively charged, and because of their small deflection, he postulated they had a relatively high mass. And then beta particles were deflected away from the negative toward the positive, so he said the beta particles had a negative charge, and because of their relatively large deflection, he postulated they had a low mass. And then looking at their penetrating ability, with the same radioactive source, you can expose them to things like paper or cardboard, and the alpha particles would be stopped by those, but the beta and gamma would go straight on through. And then things like thick clothing or wood, the beta particles would be stopped, but the gamma would go straight on through. And then thick, dense matter like lead or concrete, most gamma is stopped, but some can penetrate through. So it would take really thick concrete or really thick lead to stop the gamma rays. Okay, we'll leave this next part for the next video.